Hello, and welcome to our first video covering topics in section 1.2. In this video, we will discuss how to matricize linear systems. We will discuss the concepts of row operations, reduced row echelon form, and the Gauss-Jordan elimination algorithm. Note that matricize, matricization, and matricizable are all trademarks of the Dr. Hagen for Linear Algebra and for America Corporation, and are most certainly not real words that any other mathematician would recognize. All right, now let's matricize a linear system. First, let me just say, if you solve enough systems of linear equations, they all start to feel the same. That really, you're just applying the same techniques in the same order, only the numbers change from problem to problem. And you and I are not the first people to have recognized this. In fact, for thousands of years, people have organized the relevant information from a system of linear equations into a matrix. So let's do that. So here's a system of linear equations I pulled from your textbook. And in this system, we've got, three equations and three unknowns. And let's organize the relevant information, namely just the numbers, into a matrix. So here we've got, essentially, you think of each row gives you the coefficients or the constants in an equation. So this first row, we have 2, 8, 4, and 2 are our constants, and so those are the constants in the first row. And so each row corresponds to an equation. Another way to think of it is each column corresponds to a variable. So this first column gives you the coefficients on our x values. So we have 2, 2, and 4 are the coefficients for x, and we have 2, 2, and 4 in the matrix. And similarly, 8, 5, and 10, coefficients for y. 4, 1, and -1 are the coefficients for z. And then 2, 5, and 1 are constants, basically. So, okay, you can think of it in two ways. And sometimes when people write a matrix like this, it's always called an augmented matrix. And sometimes when people write such a matrix, they will put a vertical line to indicate where the equals sign lives. But I will say this, don't get too attached to the vertical line. In this class, we'll use it at the beginning, but then, eventually we'll just be taking matrices on their own. There'll be no vertical line, and context will be there is like what you'll have to rely on to see, to know where the equal sign is, if there is even an equal sign in the problem. But okay, that's what's called the augmented matrix, and it has all of the information from the system. But augmented sounds like it's augmenting something. And it's so called because we think of it as augmenting what's known as the coefficient matrix. And the coefficient matrix is just the matrix, but without that final column. So this final column is taken away, and it's just the coefficients of the variables. And it turns out that the coefficient matrix by itself actually can give you a lot of information, and sometimes applications only provide you with what is essentially a coefficient matrix. So we'll be using both in this class. All right, now let's talk about row operations. So the modern way to solve a linear system is take our relevant information, put it into an augmented matrix. So, for example, like we just saw. Then the second step is to translate the elimination rule. So remember, when solving a system of linear equations using the method of elimination, what we want to do is say, all right, well, what we're doing to those equations, how does that change the coefficients or the constants in our problem? And so the key step is to take the rules that we were using for solving systems of linear equations and just translate them into how are you manipulating, say, rows of the matrix. And we will go into detail in this video. And then the third step is to just really hope that you end up with a matrix that looks like this, where you've got ones on the diagonal, zeros off the diagonal when you're in the coefficient, looking at just the coefficient matrix. And you've got some numbers to the right of the equal sign. And why is that where you want to end up? Well, if you like dematricize the system now, you say, all right, well, we ended up with a matrix that looks like this. Then translating it back into equations gives us x equals something, y equals something, and z equals something, which is what we wanted. That so we get our solution. We have a solution when our matrix is in that form. Okay, so let's really dig into this step 2 and translating rules of elimination into rules for manipulating a matrix. Now, these translated elimination rules are called elementary row operations. All right, so we've got our system. And then remember, step 1 of solving it in the modern way is to matricize it. And now let's go through and say, all right, if we have an elimination rule, what is the matrix manipulation rule? So one elimination rule we have is we can always just multiply or divide an equation by a scalar. Which remember, scalar is just a number. So for example, in this first equation here, I mean, it seems like it's just begging to be divided by 2. And you can do that. You can multiply an equation, and if you multiply the whole thing by a number, it doesn't change the solutions. And what does that mean for a row operation? Well, that would just mean you're multiplying or dividing the corresponding row by the same scalar. All right. Something kind of the main trick of elimination, the thing that actually causes eliminating of variables, is you add and subtract multiples of one equation to and from another to kind of get rid of variables. And since our matrix rows correspond to equations, then adding and subtracting a multiple of one equation from another corresponds to adding and subtracting a multiple of one row to or from another. And then the last rule, which is not really important in solving for elimination, but we'll just say is legitimately something you can do, is you can swap the order of the equations. Like if this first equation actually showed up as the third equation, it doesn't change what the solutions are. So, okay, that's just something you can do. You don't really use it in elimination so much, but you will in order to kind of make things go smoothly. And when you're writing an algorithm for this, you can swap the order of rows, which is what it corresponds to. And those are really, that's it. You might think there's more going on, but truly all of elimination comes down to those 3 rules, and that corresponds to those 3 row operations. All right, let's see these row operations in action. Let's use it to solve a linear system. So in fact, let's use it to solve this one. And while we do it, let's keep track of the strategy that we're using so that we can kind of see what kind of algorithm we might be implementing. So the first thing to do is just start at the first row. And whatever row you're working on is called the pivot row, because, who doesn't like more terminology? So, okay, our first row is the pivot row. And remember, we're trying to get to a row or to a matrix where we have 1s on the diagonal and 0s off. So our first thing we want to do is we want to make that number a 1. And a row operation that'll let us do that is just dividing that row by 2. Now, this is not actually the first step in algorithms that you see for this. There's this like hidden step 1, which is it comes up because what if that number here, instead of a 2, what if that number was a 0? Well, then we can't make it a 1 because you can't multiply 1 by anything to make it. You can't multiply 0 by anything to make it 1. So our first step is actually, if necessary, swap that first row with something below it to make the leftmost possible entry non-zero, so that then you can multiply or divide to make it a 1. So, okay, first step we don't have to do because we already have a non-zero entry there. And then the next step is to multiply and divide your pivot row by a scalar to make that first non-zero entry a 1. And all right, so let's do that. I've just now written the same matrix below, but now with the first row with the first row divided by 2. And then the second row and the third row haven't changed. Now what we want, remember we're trying to get to a matrix with ones on the diagonal, zeros elsewhere. And when we're doing elimination, we're trying to eliminate variables from equations. And so our next step is we want to make these numbers 0. That corresponds to eliminating an x from the equations below it. So, okay, and how do we do that? Well, if we're doing elimination, what we would do is we would subtract multiples of our first row from these other rows. So that is going to be our third step. Sometimes this is called cleaning or clearing the column, making all the other entries in the column 0 once you've got your special one. So, okay, how would we do that here? Well, we would say if we want to clear this 2, we would subtract 2 times the first row. And if we want to clear this 4, we would subtract 4 times the first row. So, all right, let's do it. In the next matrix, the first row won't change. And now let's subtract 2 times the first row from this one. Well, okay. Subtracting 2 times 1 from 2 gets you 0, which is why we chose it. Minus 2 times 4 plus 5 is going to be minus 3. Minus 2 plus times 2 plus 1, well, I guess minus 4 plus 1 will again be minus 3. Minus 2 times 1 plus 5 will be positive 3. All right, let's now check out this third row. Let's subtract 4 times the first row from the third row. So, all right, minus 4 times 1 plus 4 is 0, like we wanted. Minus 4 times 4 is 16 plus 10 is minus 6. Minus 4 times 2 is minus 8. Minus 1 is minus 9. Minus 4 times 1 plus 1 is going to be minus 3. Okay. Now what? Well, our next step is to move down, make now our second row the row we're working on. So we'll call that the pivot row. And then we kind of repeat the previous steps. Remember, our goal is we want ones on the diagonal. So we want to make that guy a 1. And if it was a 0, then okay, maybe we would look for a row below it and swap if necessary. But we don't have to swap to make that a 1 or to make that non-zero. So okay, we jump to step 2 in our algorithm. We will, to make that a 1, we will divide the whole row by negative 3 and end up with this matrix where, okay, first row didn't change. I didn't change the third row. All I did was divided that second row by minus 3. And now, jumping to step 3, let's clear the column. Let's eliminate y from the other equations. So we want to make those two numbers 0. And we'll do it by taking multiples of row 2 and adding or subtracting multiples of row 2 to these other rows. So here, for the first row, we will subtract 4 times row 2 in order to clear that 4. And on the last row, we will add 6 times row 2 to the third row in order to clear that minus 6. So, okay, let's put that up at the top. And let's go through these row operations. So, okay, this second row isn't changing at all. And we are subtracting 4 times the second row from the first. So, all right, 0 times negative 4, 0. Subtracting that from 1 just leaves 1, which is good. We didn't want to mess up that 1 because that 1 was what we wanted. So that doesn't change anything. All right, minus 4 times 1 plus 4 gives us 0, which is what we wanted. Minus 4 times 1 plus 2 gets us minus 2. Minus 4 times minus 1 plus 1 gets us 5. And now we'll look at the third row. Again, 0 times 6 plus 0 is 0, but that's good. We wanted to leave that as a 0. 1 times 6 plus minus 6 gets us 0, which again is why we chose 6. 1 times 6 minus 9 is going to be 3, and then minus 1 times 6 minus 3 will be minus 9. Okay. Now, let's jump ahead. We want to make that a 1. There's no way to swap it with anything. So, all right, making that a 1, we'll just divide that row by -3 in the home stretch here. So that just the first 2 rows didn't change, and I just divided that last row by -3. And the last thing to do is clear this column. Let's eliminate the z's from the other equations. So to do that, yeah, want to make those 0. So now we're adding multiples of row 3. For this first one, we'll add 2 times row 3. For this second one, we will just subtract row 3. And that'll do it for us. So, all right, row 3 doesn't change. Now adding 2 times row 3 to this first row, well, adding 2 times zeros isn't going to change anything. That's good. Adding 2 times row 1 will clear that -2, which is exactly what we wanted. And then 2 times 3 plus 5 is 11. And now subtracting row 3, again, subtracting these zeros doesn't do anything. 1 minus 1 is 0, like we wanted. And then -1 minus 3 is going to be -4. All right, we did it. So we get the solution x equals 11, y equals -4, and z equals 3. This is tedious, which is why we make computers do this for us. But all right, it's instructive to just go through some of these examples, and you'll have to do some by hand yourselves. I'm sorry. And it's already time to stop celebrating. This is a total bummer, but you can't always get a matrix of this form, actually, which is how that makes me feel. So, okay, what's going on? What do you do if you can't get a matrix of this form? Where do you stop? What do you try to get to? Well, this is where we get the concept of the reduced row echelon form. So this is our new goal. It's if we can't get to that holy grail of matrices, then let's do what's the next best thing. It's called reduced row echelon form, forever written in abbreviation as RREF, and that a matrix is in RREF if the following things hold. 1, the first non-zero entry of each row is a 1. And that, just to throw more terminology at you, is often called the leading one, or sometimes the pivot one. Next, if a column contains a leading one, so a column now contains a leading one, then all other entries in that column should be 0. That's the clearing of that's eliminating the variables, essentially. And then lastly, if a row contains a leading one, then each row above it contains a leading one to the left. So let's start by just confirming that the matrix that we ended up with, our original goal that gives us our exact solution, let's confirm that that is in reduced row echelon form. So, all right, let's see. Is the first non-zero entry in each row a 1? Well, in this row, first non-zero entry is a 1, first non-zero entry is a 1, and first non-zero entry is a 1. Good. All right, now let's check if a column contains a leading 1, and the leading 1 is the first non-zero entry. Then all other entries in that column are 1. So, okay, here is a leading 1. So now let's check the column. And all the other entries are 0, so we're good. In this row, here's our leading 1, the column corresponding to that. All the other entries are 0, so that's good. And in the third row, here's our leading 1, and in that column, all the other entries are 0. No leading 1s here, so we don't really care what's happening there. All right, that second condition is satisfied. And then finally, we're saying if a row contains a leading 1, then each row above it contains a leading 1 to the left. All right, so let's start at the bottom now. All right, this row contains a leading 1, and do the rows above it have their leading 1s to the left of it? You're darn right they do. Similarly, you start at the second one. All right, the rows above it, leading row to the left. And here, no rows above it, so you don't have to check. All right, so all those are satisfied. So good. Reduced row echelon form does describe what our original goal was, but it's also broader in case we can't get to our original goal. So let's look at another example. What if we had a matrix like this? Is this in reduced row echelon form? Well, okay, let's see. The first non-zero entry in each row, is it a 1? Well, here's the first non-zero entry. It's a 1. Non-zero entry, the first one is a 1. And here, the first non-zero entry is a 1. Good. All right. If a column contains a leading 1, then all other entries in the column are 0. All right, let's go here. This is our first leading 1, and this column, everything else is a 0. Good. Here in this row, here's our leading 1. Everything else is a 0. Good. Here, now our first column, our first non-zero entry is the leading 1 here. Everything else in that column is 0, so we are good. Here's a 1, but it's not a leading 1, so we don't have to worry about it. So that is good. All right, now the last thing we want to check, if a row contains a leading 1, then each row above it contains a leading 1 to the left. Well, in this last row, here's our leading 1, and in the rows above it, the leading 1s both show up to the left of it, so we're good. Similarly, with row 2, the leading 1 in the row above it is to the left. So, all right, this is in reduced row echelon form. I want you to think a bit about why reduced row echelon form is the next best thing. And so this is something we will discuss in class, but just as a heads up, think about, when you translate back, is this where you want to end up when you're just dealing with equations? All right, and now our last topic, the Gauss-Jordan elimination algorithm. So, okay, remember that strategy from before where we have our 4 steps? Yeah, that one. Well, following these steps until your matrix is in RREF, that is known as Gauss-Jordan elimination. It is what computers do when they are solving systems of equations. And it is, it's the most widely used algorithm for doing so, for solving such systems. Actually, I shouldn't say that because there are other algorithms. But all right, it's everyone's first algorithm for solving systems of linear equations using matrices. All right, see you in the next video.